All right, a couple quick things we want to talk about here. First is increasing and decreasing functions. This is just definitions. We can use these definitions for a variety of proofs, but let's talk about the idea of an increasing function. If f of x1 is less than f of x2 for all x in the interval where x1 is less than x2, function has to be increasing. Pretty straightforward. This is equal to 6, and every value of this function is slightly less than the one before it, or perhaps a lot less than the one before it. But this is an increasing function, and the usefulness of this is that we know that if a function is increasing, then this value up here must be an absolute maximum. Um, um, it's just it's a definition. It's increasing, therefore the last point in the interval has to be the absolute maximum. Conversely, if f of x1 is greater than f of x2, same limitations for all x in the interval, x1 being less than x2, then the function must be decreasing. And therefore, the point on the right must be an absolute minimum. Why do we need to know this? Well, in math, it's not enough to just say that something is true. We have to prove it's true. So what we've done here is we have proved that it has to be an absolute maximum if we define an increasing function and show that this is in fact an increasing function. We don't have to dive any deeper. We could say, well, then therefore that's an absolute maximum. One of the fun things about math is that a lot of the time things that we just take for granted, we still have to prove them in math. So corollary, you choose number one is that if a function is increasing, then the derivative is greater than 0 for all x in the interval. And if the function has a derivative greater than 0 for all x in the interval, then the function is increasing. Converses of each other. But again, we can assume that if it's an increasing function, then the derivative must be greater than 0. We can assume that if the derivative is greater than 0, then the function must be increasing. That's number one. And again, we'll just use these to prove things. We'll say, yeah, look, there it is. Function's increasing. We know the derivative must be positive. Number two, if the function has a derivative of 0 at each point, then the function itself must be a constant. It is neither increasing nor decreasing. Neither increasing nor decreasing, therefore it must be a constant function. So that's a nice little add-on. And number three, sorry about my writing there. That's an O. Says that if the derivative of one function is equal to the derivative of the other function, then the first function must be equal to the second function plus a constant. We know that the constant has a derivative of 0, and so therefore two functions that have the same derivative aren't necessarily the same function, but they are the same function plus some constant value shifted up or down. And just a quick example of that, if we know that the derivative of something is equal to 2x, we know that the function itself must be equal to x squared, just from experience, plus some constant value. And this is called, new term, an antiderivative. We took the derivative of x squared to find the slope. The derivative of x squared is 2x, therefore the slope of the function at any given point is 2 times the x value of that point. Working backwards, the antiderivative says if we know the slope, then we can find the original function. And an antiderivative will always have that constant value right there. So take a quick second and jam that into your memory banks. The antiderivative will always have a constant value at the end. Okay, that is the rest of 5.2, not including some of the examples, but pretty basic, I think, definitions and some corollaries or corollaries that flow from those definitions of increasing and decreasing functions. All right, thanks for watching. Hope you learned something.